Okay, good morning. Today we are going to see how to derive the wave equation for light. We will be first discussing Maxwell's equations. Of course, it is an entire course itself to derive these Maxwell's equations. And I'm sure that you may have seen Maxwell's equation in some form if you have studied electrostatics. If you have not yet taken electrodynamics, whenever you take electrodynamics, maybe you will see more formal and more differential forms of Maxwell's equation. Basically, Maxwell's equations are describing electric fields and magnetic fields. So we are going to look at a special case of Maxwell's equation, and by special case I mean we are looking at a region of space where there are no free charges. So no free charges, right? And if we look at such a space, the first Maxwell's equation is essentially Gauss's law. So what Gauss's law tells you is how the electric field diverges, or it talks about what is the flux of electric field. For example, if I have a let's say a positive charge here, right? Then to plot the electric field lines, you get a test charge, right? A test charge is basically a hypothetical unit charge that you're bringing close to this positive charge. So the test charge is a positive charge, a positive unit charge, 1 coulomb. So 1 coulomb is a lot of charge, but we're doing this hypothetically, right? So if you were to bring this positive unit charge near this plus q, it would be repelled. So the electric field lines would point this way, right? So for a negative charge, they would point the opposite way because it would attract the test charge. So now the Gauss's law, that basically it's talking about the flux. So if I were to, of course, this is in 3 dimensions, right? So if I were to enclose a charge in a volume, for example, let's say, let's draw a cube here, right? If I were to draw a cube, right? So this positive charge, let's say, is sitting inside this cube, and I'm looking at the surface that is enclosed by this volume, this 3D cube. So I'm just looking at the surface that is enclosed by this 3D cube. So just the surface of the 3D cube, right? So not the entire volume. We are looking at the surface that is enclosed by a volume, and that's very important when you look at the integral form of Gauss's law. But here, basically, when we say the flux, we are basically looking at how much electric field is coming in to this surface and how much electric field is going out. So we're essentially counting the number of field lines, electric field lines that are coming in, and the number of field lines that are going out. So we can get the net flux going out minus going in, right? And that net flux basically tells you what kind of charge is inside, is bounded inside, is enclosed by this 3D volume, right? So here there are 2 things. We are taking a 3D volume, but we are looking at the flux that is going through the surface enclosed by the 3D volume. It's important to note this because the surface itself would be 2-dimensional. The surface enclosed by a cube would just be, for example, this is 2-dimensional, right? So it's essentially looking at the flux, and so the flux is directly proportional to the amount of charge that is enclosed, and it sort of comes out obviously when you do electrostatics. And we are here for deriving the wave equation. We are considering a special case where there are no free charges. So if there are no free charges, the differential form of Gauss's law looks like the divergence of the electric field. The divergence is basically essentially a derivative, right? So so we have this to be 0 because we are considering a region of space where there are no free charges, right? So this is an operator, right? This is an operator that basically is a vector operator, dou by dou xi plus dou by dou yj dou by dou zk. You're looking at the spatial variation within the electric field and making it a vector. And when you have, this is a vector and this is another vector, electric field has a direction, so it's a vector. So when you take the dot product, this is the dot product, the dot product of two vectors gives you a scalar, right? So dot product, that's why is often called a scalar product, right? So here because we have no free charges, it is 0, but if you have charges, it would be equal to rho by epsilon naught, where epsilon naught is the permittivity of the free space and rho is the charge density. This would be the charge density, right? So that's the first Gauss's law, del dot E is equal to 0. Then the second one is to do with the same divergence of magnetic field, and this one is easy because if you take any magnet, for example with north and south poles, and if I break it into half, so I would get two halves, one half and the bottom half, but this top half would have its own north-south poles, this would have its own north-south poles. No matter how small I break them to be, I will always have a north pole and a south pole. In other words, magnetic monopoles do not exist. So any magnetic field line that is going away from this basically comes back onto the south pole. And unlike charges, because we always have both north and south poles, any magnetic field line that is leaving from the north pole ends up on the south pole, right? So because of that, magnetic field lines are closed loops. So unlike electric field lines, magnetic field lines are closed loops because you always have a north and a south pole. There are no magnetic monopoles. So if every line that is going out is coming back in, the net flux is 0, or we write that as del dot B is equal to 0. So that's the first two equations of Maxwell's equations. Then the next two equations have to do with what we call as the curl, or how the magnetic and electric fields are varying spatially. So this tells you the spatial variation in magnetic and electric fields. It tells you how the electric field, for example, if you have an electric field, right? This curl is telling us how this electric field is spatially varying, dou E by dou X, right? So essentially, to give you a very brief view of what happens is that if you have a current, for example, if I have a current, if I have charge flowing in a wire, right? Let's say this wire is connected to some battery somewhere, right? And there is charge flowing in this wire, so we have current. And you may have heard from this very famous experiment from Oersted that any current carrying wire basically has magnetic field around it. Magnetic field. So a charge that is flowing, right? Charge has E field, right? Charge has electric field, and as the charge is flowing, it creates a magnetic field, right? Similarly, if you have a magnetic field, let's say if you have a constant magnetic field, for example, let's say you have a magnetic field that is pointing into the screen. This is how we depict that. This is a magnetic field that is pointing into the screen. And if I were to bring a loop, right? If I were to bring a loop, just a copper wire loop, let's say, right? And if I were to just introduce this into the magnetic field, the net amount of magnetic flux or the amount of magnetic field that's going through this changes as I drag this copper loop, say, through the magnetic field. As I drag it through the magnetic field, the magnetic flux going through this copper loop changes, because here the magnetic field is 0. When it is inside here, the magnetic field is not 0, and again here it is 0, right? So if I do that, again, this is Faraday observed this, that you basically end up producing a current in the loop. So if you change E field, like in a current carrying wire, you get B field, and if you change the B field, you get E field. So the next two Maxwell's equations are essentially relating how a change in E field is leading to a B field, and vice versa. So to write the differential form, it would be curl of E. This is telling you the spatial variation in electric field gives rise to a time varying magnetic field. And similarly, spatial variation in the B field gives you a time varying electric field. This mu naught is the magnetic permittivity, and this epsilon naught is the electric permittivity. And as we will soon see, the speed of light is essentially 1 over square root of mu naught epsilon naught. So recall that I mentioned earlier that the B field is much weaker than electric field, because they're related by the speed of light, that roughly B is equal to E by C, right? And that's why it's much weaker, and that comes from basically sort of is embedded into this equation, right? So what does this curl mean? For example, if I have an electric field, or let's say if I have a magnetic field, right, that is, I can write this as Bx component I plus By component J plus Bz along K, where I, J, K are unit vectors, right? And then I can write my curl as dou by dou xi plus dou by dou yj plus dou by dou zk, and this curl is nothing but a simple cross product. So to do the cross product, you would do ijk, right? And basically the curl is dou by dou x, dou by dou y, dou by dou z, and the components of b, bx, by, bz. This gives you the curl, this determinant will give you the curl of B. If you have any other vector, for example, instead of magnetic field, if you have electric field, instead of Bx, By, and Bz, you would simply plug in Ex, Ey, and Ez. So let's go to the next slide and quickly write down all the four Maxwell's equations. And again, remember that we're considering a region where we have no free charges or no free current. Right? So the first one is Gauss's law, because we are considering a special case where there are no charges. The net flux in electric field is 0. Right? The net flux in electric field would be non-zero if you have some charges, and in case of charges you can have isolated charges. So this need not be true. The Gauss's law that divergence of E is equal to 0 need not be true always. It's only true when you have no charges. Right? So we are making that assumption that we are looking at a region of space where there are no free charges. Right? Bear that in mind. And in the second equation is the same thing, divergence of B, but this is always true that the divergence of B is 0 because you don't have magnetic monopoles. Any magnetic field line that's leaving the north pole is always going to end up on the south pole. So magnetic field lines are closed loops, so the divergence of B is 0. And the next two equations are relating how the spatial variation in electric field is related to the temporal variation of magnetic field, or vice versa. So this curl is giving you the spatial variation. Curl of E is giving you the spatial variation, and that's equal to minus dou B by dou T, and curl B is equal to mu naught epsilon naught dou E by dou T. And then for simplicity, what we are going to do is we are only going to pick, we want to look at light. And in case of light, as we had seen in the previous lecture, electric and magnetic fields are perpendicular to each other, and they both are mutually perpendicular to the propagation, the direction of propagation. So for example, if I have a three-dimensional axis, three-dimensional coordinate system like this, so x, y, and z, if I have an electric field that's pointing this way, if this is my E field, right, then the magnetic field is pointing perpendicular, right, and they're propagating in this direction, right? So this is the magnetic field and this is the propagation direction. So E and B and the propagation direction are mutually perpendicular, and that's why light is a transverse wave. That the variation in E and B fields is perpendicular, mutually perpendicular to the propagation direction, which is indicated by K. We'll see what K is in a moment. So now let's look at the third one in a little more detail, right? So if I make an assumption that we are, not an assumption, but for simplicity, if I consider E field that's only along the y-axis and B field that's only along the z-axis, right? These are mutually perpendicular, right? One moment, I'm sorry, I would like to clarify that this K is different from the unit vector K that's along the z-axis. This is the wave vector, which we will see in a minute. Sorry for that detour, but I had to quickly clarify that. So we're looking at a simple one-dimensional variation of E and B fields. So this EY is not necessarily a constant. It's varying. It's not a constant number, right? So you have both spatial variation and temporal variation. That is, when you look at light wave, you have both spatial, that is, electric field is changing, is not just a constant. EY is not just a constant number. So it's varying in space and it's also varying in time. So you have both spatial and temporal variation. So when you see light wave drawn like this, right? For example, if this is the E field, right? The E field is varying, right? But this is just a snapshot, right? So you sort of have to imagine the spatial variation propagating in time, right? So this is basically E versus T, but this electric field is also varying in space as well as time, both, right? So the curl E, when we look at curl E, this is what is telling us about the spatial variation in electric field. So let's go ahead and calculate what curl E is going to be. For example, with in case of EY, right? So like I said, the way you would calculate curl, right? The way you would calculate curl E would be, you simply take the determinant, right? I, J, K, these are the unit vectors, and the operator, del operator, is dou by dou x, dou by dou y, and dou by dou z, and E is only along the y-axis, so we're only looking at EY, right? So if I were to do that, basically I'm going to get along the x-axis, right? I'm going to get dou by dou y, right? And this is 0, so I would get dou by dou ey by dou z, right, along I, right, and plus I would get dou by dou z of 0 and dou by dou x of 0. So the y component is 0 anyway, and the k component I would get basically dou by dou x, dou ey by dou x, right, and the next component is 0 because this is 0, so I would get this, right. So so this is what we would have, right. But recall that we have chosen our magnetic field to be only along the k direction, so we're only considering a one-dimensional case. So in this case, basically we have this, right, dou ey by dou x, which is the one that is along the k direction, like the magnetic field here, right. So this spatial variation in x, this should be x, is what is leading to minus dou b by dou t along z, right. Recall that we had chosen our magnetic and electric fields to be along y and z axis, and the third equation tells you that curl E is equal to minus dou b by dou t. So for a one-dimensional case, we see that that curl E is equal to minus dou b by dou t basically boils down to this, right. We're not looking at the x component because we are making a simple, we're going for a simple case where we're considering magnetic field only along the z axis, right. So that's why we are taking only this one, this component. So similarly, what you could do is you could do curl B as well. So if I do curl B, I would get again I, j, k, and dou by dou x, dou by dou y, dou by dou z, right? And I have 0, 0, bz. We're considering only the magnetic field along the z axis. So for this, the I component would be dou y by dou z, right? Dou bz by dou y, right? That's I. The y component would be dou by dou x of bz. So dou by dou x of bz. There is a negative sign here because the first term should be this, dou by dou z of 0, minus this, dou by dou bz by dou x, right? So this first term is 0, minus this gives you a net negative sign. And then the last term is basically 0 because you have two zeros here. And again, we are only basically looking at our electric field is only, we're looking only at the y-axis, that we have chosen to look at only the electric field along y-axis and magnetic field along the z-axis. So our curl B, which is minus dou bz by dou x, right, is essentially equal to mu naught epsilon naught dou E y by dou t, right? And I can move this negative sign there. So I could write dou bz by dou x is equal to minus mu naught epsilon naught dou E y by dou t, right? So again, we are doing a very simplified version of Maxwell's equations to derive the wave equation. Nevertheless, I think it gives you a sense of where the wave equation comes from. So so what we have now is basically we didn't do anything with del dot E is equal to 0. We didn't do anything with del dot B is equal to 0. But we have reduced the curls to a one-dimensional case, and that is dou Ey by dou x is equal to minus dou B by dou t, and then we got dou B z by dou x is equal to minus mu naught epsilon naught dou E by dou t, right? So now if I want to take the if I want to do a partial derivative of dou by dou x on equation number 3, right, dou ey by dou x, right, this will give me dou square e y by dx square. But on the right hand side, I would be doing dou by dou x instead of dou ey by dou x. From equation 3, I could write, instead of this, I could write this, right? So I would write minus dou b by dou t, right? If you consider the space and time to be that you could do a spatial derivative first and then do the time derivative, it doesn't alter the net result, because whether you do dou by dou t first or dou by dou x first, it should not matter. So because the time and the space components are basically independent of each other here, you can separate them. So if I were to do that, then I could do minus dou by dou t later and do dou by dou x first. But from our equation 4, I know what dou by dou x is, so I can plug that in here, right? So let me do that on the next slide. So here we have on the left hand side we have this, on the right hand side we have this, and I'm going to plug this in, this equation 4, into dou b by dou x, right? So I'm going to just rewrite this on the next slide. So I have dou square ey by dou x square is equal to dou by dou t of we had minus sign here and dou b by dou x, so a minus sign and dou b by dou x, and this is along z. So then I can write minus dou by dou x from equation number 4 in the Maxwell's equation. We got dou e by dou t, right? This is t. So there is one negative sign, another negative sign, so that becomes plus. Mu naught epsilon naught are just constants. Dou by dou t, so you get dou square e by dou t square. So essentially we got dou square e y by dou x square is equal to mu naught epsilon naught dou square e y by dou t square. And this is the wave equation. This is how the electric field is varying in a light wave. And you can do a similar thing for B field, for the magnetic field as well. But the thing that you must realize here is the electric field is varying in space and time. It's not just variation in time. The electric field is both varying in space and time. And this mu naught epsilon naught is 1 over c square, where c is the speed of light, right? So if I plug that in, then I can rewrite this equation as dou square e by dou x square is equal to 1 over c square dou square e by dou t square, right? And this is basically the wave equation for light. And you can write a similar equation for magnetic field as well, which is basically dou square b by dou x square is 1 over c square dou square b by dou t square. So in the previous, to derive this equation, we started with equation 3 and then plugged it in equation 4. If you do the other way around, if you start with equation 4 and plug in equation 3, you basically get the same equation for magnetic field. The important point that I want you to take home here is not the derivation of the equation here, because what we did is a very, very crude way of deriving this. Nevertheless, what I want you to take home is the thing that electric field is varying both in space and in time. Somehow when you just look at those pictures of electric field, one snapshot of electric field, when you look at this EM wave pictures, it doesn't quite give you, it doesn't quite capture both the spatial and the temporal variation of fields very well. So if you solve this equation, the solutions to this equation are essentially the solutions to these equations are essentially giving you electric and magnetic fields. So the solutions to these equations the solutions to these equations are essentially electric field is equal to E max times cosine kx minus omega t. So this k is what we call as the wave vector that we have discussed in the previous lecture, and this omega is the frequency or the angular frequency, right? To put it more precisely, so to put it more precisely, sorry about the slides changing randomly there. So to put it more precisely, we have cosine kx minus omega t. In cosine kx minus omega t, this k is essentially 2 pi by lambda, where lambda is the wavelength, and this omega is 2 pi nu, where nu is the frequency, right? So this lambda is the wavelength of light, and this omega nu is the frequency of light. So that's where the Maxwell's equations come from. Maxwell's equation, the wave equation of light, comes from, right? Okay.